Hello, students. I welcome you all for this lecture series on solar energy. This series will contain nearly about 5 lectures, and I will be covering different aspects of solar energy, starting from introducing solar energy, then how solar cell works, what are the parameters that affects the efficiency of solar cells, what are the commercial solar cells that have been available, and in last I will look into solar thermal based energy devices. So this is part of your energy studies course of unit 3. Okay, so today we'll just cover the introductory part of solar energy. So as I've mentioned in my all my previous lectures that solar energy is the main form of energy on this earth surface, except for geothermal, tidal, and nuclear energy. Most of the other energy resources are actually converted form of solar energy. So it's very important to understand this main source of energy that we receive from sun. Okay, so let's talk about the potential of the solar energy, as there has been always a big matter of debate that there will be a energy crisis that will be created in near future just because of all the energy resources in form of gas, petroleum, fossil fuels, uranium will get over, and then we will be have no energy left. But if you see this energy distribution, our energy usage per year is about 16 terabytes. This has now increased to 18 to 20 terabytes. So if we now look at the energy resources that we have, let's say tides, which produce up to zero point 0.3, geothermal can produce up to 2 terawatts, hydro, biomass, wind energy, which is up to 25 to 70 terawatts per year. This is the potential that it has to produce energy. Okay. Now, if you look at the natural resources which are non-renewable, we have about natural gases, petroleum, uranium, and coal. Okay, these are the tons that have been available with us, and which are actually been currently used to produce our energy for the daily uses. So it is a matter of debate that this resources will get finished, and we will be no energy left. But if you look at this bigger circle, actually bigger circle demonstrates the amount of energy that we receive per year from sun. So solar energy is basically giving us 23,000 terawatts of energy per year. Okay, even if you divide this number with 365 days, still we are much higher than our yearly usage. Okay, so even if we actually collect the solar energy even for few hours, and if we can store it, and we can generate electricity for the whole year. So this is the huge potential that solar energy has, that we will never face energy crisis. The only thing that we require is to convert this solar energy into the usable form. That is what is been required. There is no such as such of energy crisis, and we know that energy cannot be created or destroyed. So whatever energy that has been actually received from the sun is actually been stored on the earth. So we have to just know or develop technologies, devices to convert the solar energy into our usable form, which is electricity and the chemical fuels. Okay, just to mention one more sentence in this is that the amount of solar energy that is reaching the surface of our planet is so huge or so vast that in 1 year that we receive this energy is twice as much as will ever be obtained from all the earth's non-renewable resources such as coal, oil, natural gas and uranium. So if you just combine all these natural resources, okay, it is actually half the energy that we receive within 1 year from sun. So it has huge potential. We just can't make any comparison of the solar energy with other form of energy. So it is. And if you in your lectures you have seen that the fission of uranium can produce huge amount of energy. Okay, one fission can produce nearly about 200 MeV of your energy, which is incredible. But even higher than that, the sun can send energy to the earth's surface. Okay, so this is the most important form of energy that we receive, and our whole ecosystem actually basically run on this energy. We have to only know how to convert this. Nature has been doing it for us. Okay, technological point of view, we have to also do it by our own by using different materials. So that is what our lectures will be, that how this solar energy will be converted into the usable form directly. Okay, by using solar cell or solar thermal devices. So that is what basically this lecture series will cover. Now, exactly what is solar energy? Solar energy, as you know, that we receive on this Earth surface is in form of mostly radiation or thermal energy. Again, thermal energy is basically IR radiation that we receive. So it is part of electromagnetic radiation. Now, how this electromagnetic radiation is being produced? Okay, it is produced through a fusion reaction on the sun surface. Okay, so you have gone through the lectures on nuclear fusion, where deuterium and tritium atoms fuse together to form helium, okay, which during this process a lot of energy that has been released. Similarly, on the Earth's surface, there are many such reactions have been taking place, mainly with low atomic number atoms, mainly hydrogen or hydrogen deuterium, hydrogen tritium. This all combines or fuse together to release huge amount of energy, and this released energy reaches the earth's surface in form of radiation. And what are the constituents of the radiation? Is mainly the visible light, IR light, infrared, ultraviolet light. Very few part is X-rays, and very few part is microwave and radio waves. Now the important thing is that for us is how we can convert this radiant energy into electrical energy and thermal energy. Okay, so this is what our job is. Nature is already sending us a lot of energy in form of electromagnetic radiation. We have to just convert it into our usable form of energy. So now let's try to understand first what are the different electromagnetic radiation that have been there in your solar spectrum. So this is the solar spectrum here, okay, and it contains actually three layers. You can see this line here. There is a yellow part and then the red part. The yellow part is the direct sunlight that we can receive without the atmosphere. Okay, so if we compare this with the line, which is nothing but a spectrum of a black body. Okay, the spectrum of a black body which is heated at a temperature of 5250 degrees centigrade. So actually nothing but sun is like a black body which is heated at certain temperature and which releases the energy spectrum, okay, which releases the radiation having energy spectrum similar to that of this black body. So you can see it is perfectly matching it. So this actually defines the temperature of our earth surface, sorry, of our sun surface as well. Now this red part is the actual solar light that we receive on the earth surface. Okay, it contains 8% of UV, 42%, 42.3% of visible light, and majority of this is IR radiation, which is 49.4%. While there are few part also contains microwave radiation of 0.3%. Okay, now as I have told you in our experimental physics lectures that certain molecules absorbs IR light and excites its vibration levels. Okay, if you remember the lectures on Raman spectroscopy and FTIR, where by just absorbing IR light or the scattering of visible light, the vibration levels of a certain molecules get excited just because the vibration level matches with the wavelength of the IR light. So you can see here there is a certain valleys that have been created. That means that this light here is being absorbed by your H2O molecules, while this light is being absorbed by, or this wavelength is being absorbed by your O2 molecules, while some of your light is been also absorbed by your CO2 molecules. So these are the basic constituents of your atmosphere. H2O, which is in form of water vapor, oxygen, carbon dioxide, which can be excited by this IR light, okay, in which vibration levels can be excited by the IR light, and that is the reason this kind of wavelengths have been missing from the solar spectrum when it reaches the earth's surface. Similarly, there is also UV light which has been absorbed by the ozone layers, okay, on the topmost part. And so this is the actual spectrum that has been released by the sun, okay, or let's say it is reaching the earth, but because of the atmosphere, the spectrum, some of the wavelengths have been missing, which is absorbed by your atmosphere. So this is basically your solar spectrum with, it is called as AM 1.5. AM is atmosphere 1.5. That means if we consider the thickness of the atmosphere 1.5 times the diameter of our earth, then this kind of radiation is expected. So I have discussed this in our previous lectures as well. So this is called AM 1.5 radiation. So or solar spectrum that is been received on the earth's surface. Now how much amount from this is been reached to the earth's surface? If I consider the 100% solar energy which is coming from sun, there is two parts here which has been not reaching. One is reflected and one is absorption. So reflected from, you can see your atmosphere is about 6%. Then there is also some reflection from your clouds, which is 20%, and there is also reflection from your earth surface, which is 4%. So if you just add this three percentages, this value, which is about 30% of your light is just goes due to reflection, so that is not been absorbed by the earth surface. Okay, so 30% is lost, while there is also some part of the solar energy is been absorbed by your atmosphere and by cloud, which is nearly up to 16 plus 3 19%. So 30 plus 19 is 49. So that means that 49% of your solar spectrum does not reach on the earth's surface. So how much does it reach? It's about 51%. So 51 is what we can utilize it for the energy conversion. Obviously, since when it is heated up or once it absorbs, when the earth absorbs light, it gets heated up, so it start emitting the light. So this is what it's been radiated from the earth's surface into the space. So this has been again lost, so we have to utilize this 51% which is reaching on the earth's surface. Okay, this is on solar insolation, where how we can calculate this is, there are three kind of light that is been reaching the earth's surface. One is direct light coming from sun. There is also a diffuse light, this you will see mostly when there is a cloudy weather. where through clouds you don't see direct sun, but you can have light. So that is a diffuse light, and there is also a reflected light. So our goal is to convert this direct light into usable form of light. But there are also many several research that goes where your diffuse light will be also be used as a usable form of energy. So there are some materials which can absorb the diffuse light and efficiently produce energy out of it. So there is also a lot of research that goes into this. But yes, direct light we can just convert it into our electrical energy. So to calculate the solar insolation, means how much amount of light that has been falling per square meter. Okay, how much amount of power of your solar light falling onto the earth's surface per square meter. Okay, if you remember, this problem we had already solved during our previous lectures. I just read it out for you, which is estimate the solar power per square meter incident at the equator. So we have considered equator. Okay, when we want to find out the solar power that has been falling per meter, they have given the temperature of your sun is about 5800 Kelvin, emissivity is unity, the radius of the sun is given, and the distance between sun to earth is also given. So first we have to calculate that how much amount of power that is being radiated by the sun. So if you just take the Stephen's law and use this Stephen's equations of constant into t raised to 4, so power radiated by the earth's surface, because we have to also consider the surface area of sun. So this is the surface area of the sun multiplied by this equation. We can calculate the power that has been radiated by the sun, which is about 4 into 10 is to 26 watt. Okay, so how much amount of this power is reaching to the earth's surface, considering there is a whole vacuum in the space. Okay, and there is right now no atmosphere which is interrupting with this radiation. So we just have to see the solid angle that is been sustained on the equator with respect to sun. So the solid angle will be 1 by 4 pi d square. Okay, and this will give me this solid angle, which is 3.5 into 10 to the minus 24, and multiply by power. We can obtain the, this is per meter square. Okay, so we can obtain the amount of power received per meter square, which is 1.37 kilowatts per meter square. So this is actually the maximum amount of power that can be received on the earth's surface, that to the nearest part, okay, which is equator, per meter square. Okay, so this is what is been calculated. This is called as a solar insolation. Okay, this is 1.37 kilowatts per meter square is the solar insolation calculated on the earth's surface without atmosphere. But as I have told you in the last slide, that there is a lot of loss due to absorption and reflections of my radiation. So if I don't consider the cloud part, at least the practical insolation or that we can receive on the earth's surface is approximately about 1 kilowatts per meter square. Okay, this is the maximum practical insolation that one can receive. Okay, again, this to achieve this, it's very difficult. Only in a few region it can be achieved. But in order to calculate the efficiency and of your efficiency of a solar cell, one actually considers this insolation, which is 1 kilowatt per meter square, because efficiency of solar cell is calculated by the output power that is being generated divided by input power. Now the input power is nothing but this one. Input power is 1 kilowatts per meter square. Okay, this has been utilized to calculate the efficiency of your of a solar cell. Okay, but if you consider the average insolation, see, there are a lot of geographical locations where the solar intensity changes uh, dramatically. It's like some of the places where there is no sun at all. Means like you will always have a cloudy weather there. Okay, while some place there is very abundant of sun. The places like equator, there is insolation is quite high, but places like in the poles, most of the time there is dark there in winter, so you don't see any kind of solar radiation falling at that place. And so depending on geographical locations, weather conditions, seasons, you know if I calculate the amount or the average insolation that has been received on the earth's surface is nearly about zero point 0.4 to zero point 0.5 kilowatt, which is 400 to 500 watts per meter square. Okay, this is an average estimation of the solar insolation that is received on the earth's surface by considering all the factors, geographical factors, season, weather, also the terrain. Terrain means where desert areas or the mountain areas or sea or several things. So about as an average, let's say about 500 is the half of this. It's about 500 watts per meter square of average insolation that has been received. Now, what are the different forms of solar energy that is been utilized on the Earth's surface? Okay, so if I see here, these are the natural form of energy that is been converted from the solar energy. As I've told you previously also, that except for geothermal, tidal and nuclear energy, rest of the energy resources is been converted form of solar energy. Okay, for example, hydropower. Hydropower is what? Is the rain potential energy, rain water which is being stored at the top of the mountain, which has been brought down, and we run our turbines through that. But how does the rain go up? Is due to the water evaporation by sun. There is a water evaporation, or the sea water evaporation from the sun, which forms cloud, and then through that cloud we get rain. So it is also directly connected to solar energy. What is wind? Wind is nothing again but you have a difference in temperature. Because of the solar energy, there is a difference in temperature that is been created at different places, and because of difference of temperature you create a pressure difference, and because of pressure difference the wind flows, and the kinetic energy of this wind is been converted into your electricity. Okay, this is how your, again, the solar energy is been converted into wind energy. Wave energy is the converted form of your wind energy. Biomass is the natural plants and animals, even us, we are called as a biomass. So this for us also, we are survived only on the base of solar energy. All the plants produce their structure just because of the photosynthesis reaction. And photosynthesis reaction is nothing but they use sunlight to convert CO2 and water into carbohydrates, and this carbohydrate is later consumed by animals, human beings, and used as a usable form of energy. So that means that if there is no solar energy, there is no biomass, because everything depends upon the photosynthesis reaction. Fossil fuel again is nothing but a converted form of your biomass, the biomass which has been buried below the ground for million of years, that has been converted into fossil fuel. So if there is no solar energy, no biomass, no biomass, no fossil fuel. So the biomass, fossil fuel is again connected to my solar energy. So these are all, you can see, it's a natural form of energy sources. Okay, it's all nothing but coming from solar energy. Now, the problem with this kind of forms is that the efficiency, means the conversion efficiency from solar to, let's say, wind energy is only about 1 to 2%. So if you have like 100% of your solar energy falling, only 1 to 2% is converted to wind energy, while biomass it is even less, 0.5%. Now wave energy is converted from your wind energy. So that means that if this is 1 or 2%, wave energy will be far below than these values. Well, fossil fuels is formed from biomass. If biomass is using only 0.5% of solar energy, fossil fuel efficiency is even lower than that. Hydropower you don't even calculate, because it's very difficult to calculate how much amount of solar energy is utilized to form the evaporation of water, then how much rain and other stuff. So it's very difficult to calculate. But all this natural form of energy, all this five, is able to convert only small amount of solar energy into usable form or their form. So that's the reason we have to look for the other devices like solar cell and solar thermal, which can convert directly solar energy into usable form with very high efficiency. Solar cell can convert solar energy from 10% to 45%. Okay, now it's more than that, even 47%. Solar thermal can do similar things by creating thermal energies. If we can, the devices used for this can convert from 5 to 25% of their solar energy into usable form. So obviously, rather depending on this, which is having very low efficiency, why not develop this, which can able to convert higher amount of solar energy for our usable form. So this, it's very important that we focus here, and this is the part of this lectures series. So we'll be focusing on solar cell and solar thermal, which can able to convert a larger form of solar energy. Just imagine, like out of this 23,000 terawatts of energy that we receive, even if we just convert 23 terawatts, which is 1,000 times less, okay, which is just 0.1% of my solar energy through these devices, all our energy problem is being solved automatically. There is no issue of energy at all. Okay, so people are just fighting over energy, doesn't make sense. They have to just see how this thing is being converted, how solar energy is being used. Okay, these are the devices that have just been summarized here, where energy electricity generation can be done through your photovoltaics, where your solar energy is been or the photons in a solar spectrum is been absorbed by semiconductor, which will produce electron on hole pair, and electrons flow to the outer circuit to produce your electricity. While similar kind of things can be done by using a solar concentrator, where your mirrors are used, and these mirrors focus all the solar energy onto a small area and produce huge amount of heat energy, and this heat energy is use as a thermal energy to run your turbines. Okay, so this is called as a solar concentrator bed thermal power plants. This again is used to produce electricity. So this we will be covering in a more broader way. I just wanted to summarize here just to see there are also solar thermal devices. You have already seen this solar water heaters installed in most of the hill stations, where the houses or the people require a lot of hot water, so they usually use this solar water heaters, where the water is heated in these tubes and it is collected in this tank, and which is used further. Then there is also space heating, so you can use, not for us but for western countries or the cold countries, where solar energy has been directly allowed to fall into your houses, so that the heating can take place in your house, because in western countries 30% of energy is consumed in space heating. So for them it is very useful, for this kind of thing. Then we have solar cooking, where solar concentrator or the concentrated solar is been focused into a small area, kind of this one, where your it's tea kettle, where they are actually heating the tea or making tea for the people. Most of the religious places like Tirumala and Tirupati, in Tirupati they use this kind of solar cooking, where there are parabolic mirrors which focuses the solar light onto a tube which contains water, and this water is converted to steam, and then that steam is used to cook rice. Because in Tirupati every day there are huge number of people who have been fed prasad, which is lunch, let's say, and these are mostly based on rice and other things. So all this cooking is been done by using solar concentrator, because if you want to cook for such a huge number of population, then it will be very difficult, because there will be a lot of energy consumption from your natural gases. So it is basically been done through the solar concentrator. Similarly, you can also treat water by using solar energy, because solar energy contains UV light, and UV light can kill any kind of organic pollutants or bacteria. So even if you see your water purifying system, it contains two sections. One contains UV and one contains carbon. So UV actually basically removes organic pollutants such as bacteria and other chemicals, while carbon is used to remove inorganic pollutants. So you can use a lot of amount of UV from your solar spectrum to treat water. Similarly, you can also use solar for passive uses. Passive uses means you can design a building, where you have ample amount of solar light falling into your house, and you don't need any kind of you know lights during a day period. So you use a lot of windows or a lot of roof windows, and so that the light is allowed to fall into your house, and you don't need any lights at least in a day period. Similarly, you also create design such a way that it can also have a air circulation, because you can see that when you have a different in heating, let's say this is much hotter part, this is much cooler part, so there is a temperature difference, and when there is a temperature difference there's a pressure difference, and because of the pressure difference the air starts to circulate within your house, so you also require very less amount of fans and other things. Similarly, you have greenhouse gases which can produce a good amount of agriculture. We are fortunate that we have a good atmospheric condition where we can harvest a lot of agriculture, but in western countries this is not the case. They have a lot of winter seasons, so for that they create these greenhouses where they have a transparent roof, and this solar energy being captured to create heat, required heat, humidity, and the solar energy. Then in transport sectors also there is a lot of usage of solar energy these days. You can see this is a prototype rickshaw where they have just installed a solar panel over it, and you can run directly on solar energy, this rickshaw. And there is a car which has been already been launched, but this not on a commercial availability. They have just demonstrated how solar panels can able to run this car, but this is only for a few kilometers. Then there is a drone plane where there is a solar cell which is been installed, and you can just use the drones uh, to fly in the air. There's another very important uh, application that is coming up, which is solar fuel generation. Okay, where your there are different materials that have been utilized to as a artificial leaf. Okay, natural leaf uses uh, solar power, water, and carbon dioxide to do photosynthesis and produce carbohydrates. Okay, similarly, okay, this material is kind of artificial leaf which will also do the same thing, okay, but at much higher efficiency. That the natural leaf can do it only at 0.5% efficiency, but the material that we develop can able to convert this thing by 10% of efficiency. Then it will be really good. You just do what you just take the CO2 from the atmosphere which is available, water vapor, and use the solar light and convert this thing into fuel by 10% efficiency. So you not only solve the problem of your energy generation or fuel generation, but also you will be able to recycle this CO2 very fast. Okay, so in that case this is a very good application that has been coming up. I have been also doing in my lab these things. So if you want to have a better idea how does it these things work, we have been working into this hydrogen energy, where hydrogen is been actually produced from the solar power, and it has been used in fuel cell to produce electricity. So this is again a good way of using solar energy by developing artificial photosynthesis to develop fuels. Okay, so this is a basic introduction where I've shown you a lot of applications, and what are the potentials of solar energy, and I've also shown you that what are the different radiation of solar energy that have been there in that, and how it will be utilized to a usable form. So I've given you a brief introduction on the solar energy. In the next lecture I will cover more into the basic devices to convert this, which is solar cell and solar thermal and so on. So yes, thank you. Oops.